from section 4.2.2, what is a bound charge? Okay. These bound charges were brought about in the context of finding the field from a polarized object. And while mathematically we just kind of define them out of nowhere, these are not some magical abstract thing. They are very, very much real. So I can demonstrate what these charges look like via a cartoon first. Okay, so we defined two types of bound charges. The first is a surface bound charge. This was the polarization dotted with some normal vector, and there was a volume bound charge density, which was negative the divergence of the polarization. Okay, so before we get complicated, let's do some really simple 1D cartoon. Okay, so imagine I have this material that is just an assembly of, let's say, 6 atoms. Okay, I'm drawing them as circles here because I'm saying that they're electrically neutral. So no, they're not polarized yet. I then take this string of 6 atoms and I put it in an electric field. All right, and we talked about a couple videos ago that kind of pushes the nucleus one way and the atomic cloud the other way. So I have regions that are minus and plus. I'll do this for all of my atoms that I've shown here. So there are 1, 2, 3, 4, 5, 6 atoms to start with. I have 1, 2, 3, 4, 5, 6 negative charges, and I have 1, 2, 3, 4, 5, 6 positive charges. Okay, so I haven't created any charges. And this isn't exactly what happens in defining these bound charges, but I like to conceptualize this, the existence of surface charges as saying, right, well, I can go ahead and group this, 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 and this. Those are negative and positive charges. They didn't originally come from the same atom or molecule, but those are electrically neutral groups. So I can think about that grouping leading to just rogue or unpaired charges that exist at different parts of the surface. Okay. So hopefully you can appreciate the fact that charges will go on the surface. Now, why does the bound surface charge density have this dot product associated with it? Okay, so let's make another argument. Let's extend from a 1D material to a 2D material. I'm going to go ahead and pretend here that this material is built from a whole bunch of these. Okay, so if I were to zoom in, that's what this would look like. So I have a negative charge that's here and a positive charge that's there. I will put 5 of those. 1, 2, 3, 4, 5. Okay. And I can find the total bound charge on a surface by knowing the bound charge density times the area of my surface. Okay. Now, I can take that same exact object and make a slice, kind of in a weird way, but I still have the same number of charges on each surface, right? I still have the same total charge. I have 5 of these, 1, 2, 3, 4, 5. But now, since the area of my cut, my surface has gone up, and my total charge that's stuck on that surface has stayed the same, that means that my bound charge density has changed. It's gone down. Okay, so because this is related to the size of my surface, it has to have something to do with the orientation of my surface. Okay, so in the first example over here, the polarization was to the right, and the normal vector was also to the right. Okay, since they're both pointed in the same direction, this cosine of 0 gives us 1. All right, so that's the maximum value you can get from a particular configuration for a bound charge. In this second case, my polarization is still to the right, but now my normal vector is not to the right. Normal vector is pointed something like up like that. Okay, so now whatever my bound charge density is here is less than or equal to whatever the bound charge density was there. Okay. So hopefully you can appreciate the fact that the relative orientations of surfaces affect the densities themselves, and it manifests itself through this dot product here. Okay, so I like to think about this polarization as like painting in some bound surface charge density. Okay, now what about the volume charge density? This is having to do with the divergence of my polarization. All right, and I remember that divergences, all right, if I take the divergence of some vector field, it tells me about whether there's some flow or some region of space that is being taken into other regions of space, so like a source or a sink. Right. The only way you can accumulate bound charges in is that if you have some sort of divergence of your polarization, or divergences are also like spatial gradients, right? So if you have a non-uniform polarization that acts like a source or a sink, you can get regions that have different kinds of charge densities. Okay, so let's imagine that I have some weird polarization that splits apart previously neutral atoms, or not splits apart, but stretches rather. That's 5 positive charges and 6 positive charges and 6 negative charges. All right. If I look locally, this region of space has more negative charges. All right. So I would have some weird bound charge buildup there. Okay, so that's just an example where that would be possible. So bound charges are real, and you can calculate them given the polarization.